Good morning and welcome to another Atago webinar. Today we'll be speaking about the polarimeters in the pharmaceutical industry. Okay. The first part of this presentation will be about polarimeters, but after that we want to focus on the temperature control module for Atago polarimeters. Okay, so yep, this is the polarimeters in the pharmaceutical industry, temperature controller edition. And so polarimeters are very simple instruments. In at least you can simplify it in terms of they measure optical rotation. But optical rotation in itself of different substances is a bit complicated. But basically a polarimeter measures optical rotation. Okay, an oversimplification of what it does. Polarimeters can be used, or in R&D polarimeters are used to determine stereochemical compositions. Stereochemical compositions is like the study of the relative partial arrangements of atoms that form the structure of molecules and their manipulation. So it's basically is the study of the structure of the atoms of different compositions, of different samples, of different liquids. The second way the polarimeters are used in R&D is for multirotation. This is the change of the optical rotation because of the change in equilibrium between two anomers. And also it's used for the characterization of newly synthesized chiral compounds, and also in the separation and analysis. So these are a few of the most common ways that polarimeters are used in the R&D phase of pharmaceutical industry. Okay, polarimeters are also used in raw materials, or when receiving raw materials. A polarimeter, because of the chiral effect of some substances, it can help identify what a raw material is, or which the raw material is. Not only can it help identify, but it can also help you verify the purity for control purposes. So for example, if you're receiving a substance and the MSDS or some other document or certificate, it should list different properties, whether it be density, viscosity, refractive index, or in this case angular rotation, optical rotation. Then with each of these characteristics you can use a different instrument to verify, and if one of those characteristics is optical rotation, or then you can use a polarimeter to verify that the substance you got is what the document says you got. Okay, and then the third way, or third phase, or third place where polarimeters can be used is in the manufacturing of the pharmaceuticals. This is mostly following, exclusively, almost exclusively following the pharmacopoeia. The pharmacopoeia would give you a very detailed step-by-step of what to do, how to do it, and what instruments to use. So polarimeters are not used for all products in the pharmaceutical industry. Specific products, or each product has a specific list of instruments that will be used according to pharmacopoeia. So it's not unusual for some pharmaceuticals to not need a polarimeter while others do, because it would depend a lot on what that plant, sorry, I should say pharmaceutical. It's not unusual for a production plant, a pharmaceutical production plant, to not need a polarimeter. Most of them do, but I've come across one or two that don't, and they don't because, well, they're not producing something that that requires, as per pharmacopoeia, a polarimeter for the manufacturing or the quality control of that substance. But anyways, as per pharmacopoeia, they're used in manufacturing. They're used for polarimeters are used for to measure accurate dilutions. When you're diluting, there's different instruments that you can use to confirm your dilution or to help you verify how accurate your dilution is. Polarimeters are one of these instruments, especially if you're dealing with, well, sugar is one of the common ones, or different sugars are one of the common ones, but also any substance that has a chiral effect, has a chiral effect. You can determine dilution by using a polarimeter. It's also used to determining the concentration of sugars, and sugars is a very vague use in this term. It could be sucrose, dextrose, different sugars, and it's also used for the purity control and the determination of concentrations for the different substances, raw materials that have the chiral effect, and also for the monitoring of the chemical process. Okay. So things that are these on the list are polarimeters are commonly used in the production of or the use of these things: amino acids, amino sugars, amphetamines, antibiotics, various blood pressure medications, codeine, dextrose. That's, like I mentioned before, sugar was used before, but it's a very vague term because it includes different actual sugars and dextrose. So one of these diuretics. Diuretics are used in different applications. Lowering blood pressure is one of them. But so polarimeters are used in the making of diuretics, testing hormones, proteins, serums, steroids, tranquilizers, and different vitamins. So these are commonly polarimeters are commonly used when you're dealing with these or when you're manufacturing these. Okay. So now we jump to, so what we saw before was the basically very quick intro to polarimeters in the pharmaceutical industry. Now we're going to move on to temperature control, because temperature control is very important when using a polarimeter. Temperature control will give you more stable readings, will give you more accurate readings, and that's because the temperature of the different things you're measuring, things like these, or things you're making, things like these, temperature affects the value that you'll get with the polarimeter. So you want to keep the temperature at the specified temperature as per pharmacopoeia or as per your procedures. And the closer you are to that temperature, the more accurate your reading will be, and the less fluctuation in your temperature, the less fluctuation your readings will have because of temperature. So temperature is one of the biggest factors when getting accurate and repeatable results. The more accurate the temperature is controlled, the more accurate and repeatable your results. Okay. Here we have a list of different things, different substances. The blue bar shows the error, the repeatability, the accuracy of that substance with no temperature control. For example, the first one, sucrose, with no temperature control. Obviously, this is study made with controlled temperature, room temperature at 20. But even a controlled room temperature is not as accurate as controlling the substance of your controlling the temperature of your substance. So the blue bar is no temperature control is used. It's just a temperature control room, and the pink is with temperature control. So you were controlling the temperature of your sample. As you can see with sucrose, there was a huge, almost just a bit over twice as much accuracy and repeatability was achieved when you're controlling the temperature of the liquid of sucrose. Sodium chloride, not as much difference, but it did help. And when you're dealing with different oils, you can have a huge difference. So it as you can see from here, it does help, but it does help depending on what the substance is. Temperature affects some substances more than it does others. That's why it's very important to control the temperature of the liquid. Having a temperature control room is not enough to give you a very accurate reading. Okay. The traditional way of controlling temperature would be through a flow tube or a water bath, which is what we see here to the right. Basically, you have a cell where you would inject or pour your sample into, and the wall of the cell, or inside the cell, it has a hollow wall or a chamber where water would be pumped in and around your sample to control the temperature. So you connect this device here to a water bath, and on one point of the nozzle, the water is going to go in, circulate around your sample, and then go back out to the water bath. And that is how temperature is controlled. That is what used to be the traditional way. A lot of companies are still using it because it's what they've been using for a while. It has some advantages, but it also has a lot of disadvantages compared to the Peltier system. So the Peltier system is, first of all, is a lot quicker. The Peltier can quickly control the temperature, whether you're heating it or cooling it. It can get to the target temperature quicker than a water bath. Not only get to the temperature quicker, but the startup time at the beginning of the day or the beginning of the week is quicker, because with a water bath you would have to turn on the water bath. It takes a while for the water bath to get to the temperature, and then you have to hook it up to the device you see here to the right, and you have to insert it into polarimeter, and you have to wait a while for the water bath to get to the target temperature. And then you have to see what the temperature is at the polarimeter, and if it's not the desired temperature, let's say you walk in, turn on the water bath at 20, you hook it up to your polarimeter. After 30 minutes, 20 minutes, you see that the polarimeter's temperature is 19.5. Even your water bath is 20.0. So you have to adjust your water bath by about 0.5 so that your the water that's getting to the polarimeter is 20. That way you're assured that the sample would be at 20. So it takes a little bit of time to do that, especially if you weren't working the day before. It's the first day of the week that you're working, then the setup takes more time. With the Peltier, you just turn on the instrument, turn on the Peltier, and you quickly get to your target temperatures. Almost no setup. Gets to the target temperature very quick. So one of the benefits of using the Peltier temperature control is it saves you a lot of time. The other reason is accuracy. It's more accurate, more control. More control over the temperature, as mentioned before. There's more control over the accuracy of your reading, the repeatability of your reading. It also uses a lot less real estate, a lot less space on your lab. The device, as we're going to see soon, is very small, very easy to use. The flow cells tend to be a little clumsy because of the shape, as you can see to the right. They can be a little heavy depending on the material. And yeah, it can be also a little bit expensive. And if you're looking for a specific material, let's say most of them are made from stainless steel, but if you're dealing with some acids of some material that are corrosive or react with stainless steel, then getting the flow cell in a material that's specialized might be more difficult. With the Peltier system, you don't have to change the whole Peltier, you just have to change the little tube. So it's easier. And also, like I mentioned before, the device to your right, or the accessory to the right, uses a water bath, so it takes up space. There's tubes going from the water bath to this, the tubes going to the polarimeter to get to this device. With the Peltier, you don't have that, so it takes up a lot less space on your lab, and also it's easier to handle. The Peltier is small, light, easy to use, fits in your hand basically. Okay, and one of the reasons we're introducing this is, well, it's our first one. It's Atago's first Peltier temperature control unit. And when we designed this, we had in mind you guys. We had in mind all you guys that have bought Polax 12, that have had the AP100, that's very old but still working, that have the AP300, that have the SAC. So a lot of you already have a lot of polarimeters, or a lot of different model polarimeters in your lab. Some of you from emails I've gotten don't have the Polax 12. You have a very old one that's called Polax D, that's more than 20 years old. So when we were thinking about coming up with or designing this temperature control instrument or accessory, we were thinking about the users who already have an instrument. So we wanted to make it compatible with all Atago polarimeters, and that's why it has this unique design. This unique design that you're going to see soon, it's because we want it to fit in the polarimeter you already have. So if you want to have temperature control, you can buy this accessory, but not replace your polarimeter. You can just add it to whatever Atago polarimeter you already have. Okay, and as I mentioned before, it comes in stainless steel, but we can also make it hastelloy to meet the your needs if you have any harsh chemicals or samples. Okay, then now on to the video. So this one that we're gonna see is the SAC-i temperature control. Sorry, is the SAC-i temperature control. So we're gonna see it in the SAC-i environment. Sorry, SAC-i environment. It will work very similarly in the AP300, and will work also very similarly with the Polax if you have one. The Polax, for you guys who don't recognize that one, is the analog polarimeter. Actually, it's the analog polarimeter. So it does fit on both our digital models and the analog version. But the video we're gonna see is only related to the SAC-i. Okay, so here you have the SAC-i, and as you can see, the body is just the usual SAC-i, but it has that temperature control unit that's connected to the flow cell that's inside. So that was part of the design. We wanted to fit the polarimeter you already have. Okay, temperature controller, the catalog number is 5900. Temperature range is from 10 to 50, and temperature accuracy is 0.2. Okay, it looks like a big device, but in a bit you're gonna see it's very small. I just wanted to give you the different the different parts to it. Hello. Okay, sorry. Yeah, I just wanted to give you the different parts that the instrument is breaking down. Sorry, I think I'm having some audio problems. Give me a second. Okay. So it's sorry, but basically it's divided into the fan. You have the fan filter, you have the base, you have the cover, and you have the observation tube. Okay, the SAC-i has two temperature channels. One is for the temperature chamber, the other one is for the temperature controller. So hook it up to the back to the temperature controller. There's two ways to set up. You can set it up in there, or you can set it up outside. So right now we're showing you how to set it up in there. You put the base on, then you put the flow cell.